Welcome to Industrial PLC Applications. This video is Module 1, PLC CPU Operations. The following is a generalization of the operation of an Allen Bradley Micro 850 series single CPU PLC and generally manufacturers of other single CPU PLCs. There are other CPU operational methods depending on the manufacturer and their construction, such as safety PLCs, dual CPU PLCs, redundancy systems, etc. Therefore, always read the operation manual of any PLC to be sure of its CPU processes and logic flow. Micro 850s have three operational modes. Each operational mode affects the scanning of inputs, the execution of logic, and the setting of outputs. When in program mode, the logic or logical values can be altered or rewritten. The program is not executed, so the inputs are not scanned and the outputs are not energized. When in run mode, alterations to the logic or logical values are not permitted, and the PLC's CPU has full control of program execution. When in remote mode, minor logic modifications are permitted to be made and tested, and if suitable, assembled, all while the PLC continues executing the existing logic. This is an operational mode that will not be covered in this video.
A PLC's main CPU may not have the power of your cell phone, but its lack of size and memory is actually an advantage, since it does not try to download videos or take pictures or run a large operating system like Windows, which can have constant updates that impact operation. Inputs are connected to the PLC via the Input Interface Module. On the PLC we are using, the interface module is embedded to the motherboard. The inputs we are using are called syncing inputs. They get their power from the same 24-volt source as the PLC, but block the power to the input terminal. When a normally open input changes state, its contacts close. This will then permit the voltage to be applied to the input module's terminal screw. The presence of a voltage will be detected, and the CPU will write a 1 to the input's variable or memory location. However, a normally closed device, like a stop push button, will not block the flow of electricity to the input module, and a voltage will be detected, writing a 1. When the normally closed contacts open, the PLC will not detect the voltage and it will write a 0. It is important to understand this process, especially when adding new inputs. Some inputs cannot be installed on a syncing input module. After reading the value of the embedded inputs, the CPU will then examine any expansion input modules added to its project. Expansion modules can increase the number of inputs or can be specialized like analog. The CPU then applies the values written in by the inputs and resolves the program logic stored in its memory. The embedded output module on our PLC controls any output attached to it. When the CPU resolves that an output must be energized, it closes an internal relay and voltage goes through the relay out to a terminal screw and onto the end device. Since the embedded module is the source of the voltage energizing the device, the output modules are called sourcing outputs. The module can only energize devices of the same voltage, size, and type, and it is limited in the amount of current flowing through it. Once the outputs are generated, the CPU performs some self-diagnostics and some internal housekeeping such as communication updates and readings before starting the process over again. All in all, the CPU runs a simple focused program to control automation, and it does so millions and millions of times reliably and predictably. This is essential for manufacturing and process control. As a PLC is a dedicated controller, it will perform this process millions of times repeatedly whenever it is placed in run mode. This cyclical process is known as the PLC scan, and it can be thought of as a broken circle. The run mode scan has 4 steps: scan the inputs, solve the logic, set the outputs, and perform housekeeping. Every scan begins by reading all of the inputs connected to the PLC. This includes the embedded module inputs, any expansion modules, or any input received electronically from a network connection. For simplicity, this course will only focus on directly connected I/O. Inputs can be changing rapidly, so this step takes a snapshot of the inputs and freezes their state for a single scan, which can range in time from a few milliseconds or to a few hundred milliseconds depending on the number of I/O involved or the size of the program. During the input scan, 1s and 0s were applied to the memory locations assigned to the inputs, where the voltage received at an input terminal resulted in a 1 and an absence of voltage resulted in a 0. These values are then applied to the ladder logic, rung by rung, to determine if the rung has logical continuity. The logic is resolved in a fixed order. The CPU reads and applies the inputs one rung at a time and starts at the first rung. The logical values of the inputs are applied to the logic of the rung from left to right. Then, the CPU moves on to the next rung of logic and again applies the logical values to the rung from left to right. When all the rungs are resolved, the CPU will move on to the next program and do the same thing to each program until the project is finished. The CPU evaluates each rung of logic looking for logical continuity. Logical continuity is the same as current flow in an electrical circuit. If there is a powered connection between points, power is turned on to the output. If there is no power or any break of power, then the power is turned off. With logical continuity, when there is a path of logical truth that completes a path to the output, the rung's output will be energized. In this example, 3 rungs have logical continuity. Since 3 rungs have logical continuity, a 1 is written to each output. For any rung that does not have logical continuity, a 0 is written. All of the outputs will be written at the same time after all the logic has been resolved. Therefore, outputs are the last to be written. Keep in mind that outputs are refreshed each scan. That is, changes in logical state will result in changes to the output states. But it also means that no changes in logical state will still result in writing the logic. In other words, every output is overwritten every single scan. And 0s will overwrite 0s and 1s over 1s, as well as 1s to 0s and 0s to 1s. After the outputs are set, the PLC performs some housekeeping and self-diagnostic operations for every scan. This time slice is usually very small compared to the rest of the cycle, but is important for the total operation. Furthermore, when a PC or laptop is connected to the PLC, this time slice is when the PLC updates the PC and its software as to the status of the PLC and the logic resolution. When the PLC is first put into run mode, the PLC executes the new logic and monitors the time it took to complete the scan. This scan result is then applied to a watchdog timer, with some additional time added for the housekeeping function, etc. The watchdog timer then starts with each scan of the inputs, and if the PLC's current execution of the logic exceeds the watchdog time, a major fault is initiated and the PLC stops running the program. So let's do a quick review. 1. The PLC scans the inputs. 2. It solves the logic from top to bottom, one rung at a time, from left to right. 3. After all logical outcomes have been determined, the PLC updates the outputs and then energizes them according to logical continuity. 4. Some housekeeping is performed. And then 5. Well, keep repeating the same thing until either the PLC is put in program mode or is shut down. Thanks for watching.